Good afternoon, everyone, and I thank the organizers for giving me opportunity to present about this about this work that I have started just a little bit small time earlier. So here I will just be presenting about the initial results about that we have found out in this study. So I am Arpan, and I'm currently working in Institute of Radio Astronomy and Astrophysics in UNAM. So I will be just talking about how the radio flux variability is changed with simultaneous NIR spectroscopy in the coronet cluster of Corona Australis. So this is the brief outline of the talk. So I would just give a brief introduction and then about the observations and finally some of the results that I have got, and I will conclude. So I guess this slide is everyone knows about most of the variability in the optical and infrared parts, but still I will just give a brief summary. Like in the optical and infrared parts, the most of the sources and the young stellar objects are variable because of these four factors, like on the modulation and growth and decay of the stellar spots. It can be like dippers, which can be like some of the clumps that appear in the disk can obscure the line of sight view and which can result in the dimming of the source. There can be some short scale accretion variabilities which can be known as bursters, and so several studies have shown them. And then there can be extreme accretion variabilities like FUs and XORs. However, in the radio fluxes, some of the studies that has been previously done, it has been found that these YSOs are still variable in the radio fluxes also, in the radio wavelengths. So the major function, the major reasons for the variability in the radio are the non-thermal radio flares. Those are mainly found in the most evolved sources because of the magnetic reconnections on the protostellar surfaces, or it can be between the because of the interaction of the decoupled magnetic fields at the at the inner disk boundary. Uh, the other form of variability in the radio that are observed is basically due to the accreting YSOs, which emit the thermal radio emissions from regions where the magnetospheric wind soaks the ambient gas. So because the main motivation of the study was to do the simultaneous NIR and radio monitoring observations so that we can discriminate between these above sources. So initially what so initially we started with the Corona Australis cluster because it is very close by at 130 parsec, and you can see the location also. And the other feature of the Corona Australis was that it is a very dense cluster. Like in the plane of the sky, you will find around like 25 class 0 to 2 YSOs uh, in the per parsec of the sky. So previously, one study has been done by Baobab Liu in around 2014, where they have observed this cluster in VLA 3.5 centimeter band, and they have found out the radio flux variabilities in these sources ranging from hours time scale to days time scale. And comparing it with the previous the infrared surveys, they found out that this can be because of this variability can be dependent on the within the YSOs that are dominated by the accretion by the magnetosphere and their interaction with the winds. However, the main caveat was that the radio observations were not simultaneous with the infrared observations. The infrared observations were like 3 to 10 hours, 10 years earlier than that of the than the radio observations. So what we did here is that we revisited this Corona Australis cluster, this coronet cluster again in around 2014, and we made a simultaneous observation of this cluster between in these dates. And the main motivation with the and we used the VLT KMOS observation, the KMOS instrument, the K-band multi-object spectrograph, which was then was just commissioning in that source in VLT to observe the a sample of around 28 YSOs, and also the similar field in the JVLA to find out a common consensus between the radio flux variabilities with the with the lines that are present in the K band, namely the bracket gamma emission, which is a tracer for the accretion rate, and also that of the hydrogen line at 2.122 microns, which is an tracer for the outflows, and to trace some of the relations between the infrared and the radio. And for this, we selected a total of 28 YSOs in the cluster. And alongside it, you can see these are the different KMOS observation dates and along with the VLA observation dates. So in these sources, when we analyze the data, we found out among the 28 YSOs, these are the sources which detected the bracket gamma emissions in the bracket gamma detections were there in these sources. And here alongside it, I can show you the distribution of the radio of the sources that were plotted on the Lewis 3.5 meter 3.5 centimeter VLA map. And with this, so then next of all, among these bracket gamma detections, these are the only sources which had simultaneously detected in radio and then that in bracket gamma, either in emission and absorption. So this is the latest VLA images, which are on the more higher resolution images than the Lewis paper, but it has the same RMS noise of around 8 microjansky per beam. So here you can see that though most of the features here are gone, but you can see most of the sources are more resolved here. And most of the radio images are currently worked by one of the PhD students in area, by Johanan Ramirez, and she is now calculating the flux values of these sources. So I will mainly point out about the infrared variabilities that we have observed. So among these sources, I will be mainly showing the radio, simultaneous radio, and the optic radio and infrared detection sources, the results that we have found, on the basic results. So this is one of the source, which is a class 1 source, the IRS2. So previously in NISNI in around 2010 reported that this source has an accretion rate of around around some 3 into 10 to the power minus 8 solar mass per year. So we also obtained the spectra with KMOS in the different epochs that you can see. And this source, what we found, it has a very nice bracket gamma in emission, and it had a very weak like CO band-aids in emission. But what we were expecting was some H2 emissions in the which acts as a tracer for the jets, but we could not find it. So this is some of the line profiles, in the zoomed in profiles of the bracket gamma, and along with the different dates. However, with the KMOS data, we have a problem that the absolute calibrations, absolute flux calibrations could not be done, and all the relative and all the sources, all the fluxes that are calculated here are the relative. So we are having some problems in estimating the actual value of the accretion rates in different epochs. So what we did, we are now for the time being going on with the equivalent widths. But the thing is that with the KMOS, we also have some, as it is a IFU spectra, so it has some kind of spatial information also. So what we did, we tried to calculate the moment zero maps around the sources, and here it is. The moment zero maps for the different of this source at different epochs. It can show some kind of structure in it, but most of it is PSF dominated. So so it is. We can't say much about the structure, but at least it has some kind of this kind of distribution. So what we moved on, we are now convincing ourselves that as some K-band informations are not present here for the absolute flux calibrations to estimate the accretion rate, we are just moving on with the equivalent widths. And we are trying to convince that the variations in the equivalent width reflect the changes in the accretions in the sources. And in the next one, we also looked at the neo-wise light curves of the sources, because the neo-wise light curves are, because for the younger sources, those are more detectable in the variations in the neo-wise. So this neo-wise variations that we can show is this is how the light curve and the source evolved, and in the color evolution of the sources, as you can see. And in this source, we can see that the source was mainly becoming bluer when it is becoming brighter, which we can say that, yeah, the short scale variations that we see are mainly because of the accretions, which can be the more dominant factor. And next up, I will move on to the next source, which is like the Peterson 2, which is a more evolved source. This has a typical, I guess there is some issue on the slide. Okay, so yeah, so this is one Peterson 2. This one is a more evolved source. It has a different, very broad H alpha profile, and as you can see, also it has a very deep absorption bands in the CO bandits. And what we did, we tried to look at the moment zero maps to see the variations in the moment zero maps, how to see the intensity distribution if it displayed some structures. Next up, we tried to look at the equivalent with variations in the bracket gamma and that of the I think some of the levels are not coming up in the slides. So what we did, we tried to look into the variations in the equivalent to the bracket gamma and with that of the CO. So as the levels are not coming up, I just use the point. So this is the variation in the equivalent widths in bracket gamma, and this is the variation on the equivalent width of the CO bandits. What we tried to look at if there is some correlation between them. So because the equivalent width in the bracket gamma represents the changes in the accretion luminosity, how the accretion luminosity affects the inner disk structure, because the CO bandits represents the inner structure. So what we found out that here, if this point has a very large error bar, but if we just ignore it with the or take it with the error bar in the CO, we find that with the variations with the accretion rate, we can see as expected the inner disk, there is a effect in the inner disk structure, and it changes the CO bandheads. And next up, we looked at again in the neo-wise light curves evolution for this source. This is how the source varied, and in the color evolution, we can see that in this more evolved source, we could not say that the variations are entirely because of the changes in accretion. It could be some other factors also, which gives rise to this structure, this kind of clustering in the color magnitude diagram. And finally, and then this is the another source where it has again a very nice bracket gamma emissions. And I would just move through the slides to show the results. And here also it is as it is a very young source, it can show like the variations are driven mainly by accretions. And finally, the final source, which is the most evolved source, is a class 3 source, and the radio one, which has a typical FU Oris spectra like that of it has all the absorption lines in bracket gamma also, and in the very deep bracket and the CO bandheads. So, and then moving on again, these are how the bracket gamma line profiles varied with that and the moment zero maps of the bracket gamma in absorption. And this is how the variations in the bracket gamma wind absorption profiles with that of CO bandheads and their correlations. And yeah, finally, I have the neo-wise light curves. The neo-wise light curves in this source was very variable, particularly in the W1 band. So we checked the color evolution, but we found that the color evolution in this source could not be trusted, because as you find out, as we we have seen in very many of the high mass YSO neo-wise light curves that if the slope comes out to be around 1, the the variation could not be compiled with the neo-wise light curves, which can be mainly because if we change it from W1 to W2, the slope drastically changes. So it could not be a very real variation. And the main take-home messages are this. The fourth point, which is the accretion is more dominant in the younger stages, the bracket gamma detections with the radio detections most likely points to the interaction of the magnetospheric winds with that ambient gas, and the further work is in progress mainly with the radio part of the data, and we hope to show some interesting results in some future. And thank you.
Hi, sorry if this is like a dumb question, but I missed it. I have two questions actually. So the first one is, what are exactly the variations you're talking about? Is it a change in absolute flux? You also, a lot of your plots had line width, but like, or relative width, or yeah, equivalent width, but like what is equivalent width? Like can you just say exactly what is varying?
So the point is that with the KMOS data, it has problems with the flux calibrations, and the flux calibrations are not absolute. So the variations that you see in the sources, those are more relative, not actual. So that is why we are not. We were trying very much about to find some ways to find to calibrate them to have the actual flux calibration so that we can quantify the accretion rates. Unfortunately, we could not do it here. So for that reason, we went to the next step to have a quantitative view of the accretions, and for that we use the equivalent widths of the lines.
Okay, cool. Thank you for clarifying that. And then my other question was, you had a lot of the moment zero maps, and I'm assuming this is from the VLA, correct?
No, those are from KMOS.
Okay, is that an interferometer? Just out of curiosity, I'm not familiar with that.
No, it is not an interferometer.
Okay, cool.
It is an IFU-based spectrograph.
Okay, cool. Thank you.
So I wanted to ask about these classifications. You have, these are all class 1 and class 2. Where do those classifications come from? Because if you've got this tiny little area and you've got all these fjords, that seems very odd to me. You know, it seems very, surprising that you've got this cluster of fjords. So where does those class 1, class 2 come from?
So there was one study by Don Peterson, I think it's in 2016. So in which she studied this Corona Australis coronate cluster, in which all these sources, those that were classified as class 1s and class 2s, say based on the split mid-infrared slope of the mid-infrared one as it is done. And it's based on the Spitzer study of the Corona Australis.
Lots of class 2s don't have CO unless the stellar photosphere.
Yeah. Actually, yeah, I have also seen in the same kind of sources, but I just only showed which have the relevant bracket gamma detections with the radio ones.
Yeah, maybe something related. So in the last source, you said that it's a class 3 source with the FU Oris type spectra.
Yes.
So what do you think is physically happening with that source? Like what is driving the outputs or? No?
Yeah, we just have only those few very small month scale epoch data. So we have not checked it. That is another thing we had just kept it aside to study about the FU Oris nature. Yeah.
Thanks.
Yeah, just probably comment on the question that Lee made and also the comment that Patrick asked maybe yesterday. So the classification of this region is made from the Spitzer color diagram, and we now probably don't consider that's super robust, but it's also weird that so in this region, so the source we are looking at, so these sources that are showing the bracket gamma line emission, they show very strong radio emission. So, and it seems like for most of the class 2 sources, they don't show strong radio emission. So maybe, so in some sense, of detecting strong emission at 3.5 centimeter band is another way that help you to convince yourself those are relatively young sources. They have relatively high accretion rate and relatively high mass outflow rate.
Thank you. Let's thank Arpan again.